Imagine a play area after a long day of fun, cluttered with toy cars, teddy bears, and building blocks. Cleaning up can feel like an endless task. Now, picture robots stepping in to handle it for you, effortlessly organizing the chaos. A robotic sorting system is designed to tackle this challenge. It uses advanced vision-based object detection and force-based material characterization to classify toys as hard or soft. By seamlessly integrating these technologies, the robot sorts and organizes toys into designated bins, all autonomously. This project isn't just about toy cleanup, though. It demonstrates the broader potential of tactile-based sorting systems in industrial and logistic environments. From warehouses to homes, this technology brings intelligence and efficiency to repetitive sorting tasks. With this sorting system, we aim to simplify everyday chores while pushing the boundaries of robotics and automation. Our simulation setup includes a WSG gripper attached to an Iowa arm which is welded to the table, left bin for hard and right bin for soft objects, and a bunch of objects in the play area to sort. Additionally, we have some cameras over the play area to give visual input to the arm.
The core part of our project is a tactile classification system. During the grasp selection stage, the robot visually calculates the distance between the two selected antipodal grasping points. During the post-pick stage of the picking operation, the robot measures the separation between the gripper's fingers. It then calculates the ratio of these two values. If the ratio is near 1, then the object experienced very little deformation and is thus hard. If the ratio is small, then the object experienced substantial deformation in response to gripper pressure and is soft. Experimentally, we deduced that a threshold of 0.8 is a good boundary between hard and soft objects.
Our arm starts off waiting for the objects to settle. It uses the vision system to identify a nearby toy, planning a pick trajectory to the toy, and then two possible trajectories to place the toy in each of the bins. It follows the pick trajectory to the toy, grasping around the antipodal points of the toy, and then computes the actual to planned grip ratio it has, using it to classify the toy as hard or soft. Based on the classification, the arm switches to follow the trajectory to the corresponding bin to place the object. Then the arm moves back to default position and repeats this cycle for remaining toys.
An infrequent problem when attempting to grasp a small object is the robot missing the object entirely, grasping empty air, and then attempting to put the object that it believes it's holding into a bin. Fortunately, after putting the non-existent object in the bin, the robot makes another grasp attempt at the real object, and it will keep trying to do this until it successfully grasps the real object and puts it in the bin.
Our original design plan divided up the trajectory from picking a toy to bin placement into two pick-and-place stages, with the second stage occurring after classification from the first stage, when the gripper first grasps an object. Because every pick-and-place follows a pre-planned trajectory. This led to the gripper opening after grasping the object during the first stage and before it was ready to be dropped into the bin, because the gripper automatically opens after each pick-and-place operation. We tried fixing this by adding a midpoint area for the gripper to drop the object in during the first stage, and then picking up from that area in the second stage. However, this added unnecessary complexity and areas for failure during the operation.
Ultimately, the solution we decided on was to have the robot compute a dummy placement trajectory for the initial pick operation, while simultaneously computing another placement trajectory for each of the two bins. When it classifies the object as hard or soft in the post-pick stage of the initial trajectory, it switches to either the hard or the soft placement trajectory.
Through this project, we developed a deeper understanding of the pick-and-place operation in regards to trajectory planning and handling unstable grasps. We learned to set up custom camera configurations within our simulation for greater sorting accuracy, and personalize the grasping stages in order to isolate hydroelasticity for sorting. We also learned more about the relationship between SDF object geometry and grasping stability.